The next item we're going to look at is relaxation time. And so we've kind of talked about this very qualitatively in a previous video where we said if we have free charge carriers in a metal and we apply an electric field, all those charge carriers are going to redistribute to the surfaces and none are going to be left in the volume. I had said that that happens very quickly, essentially instantaneously for a really good conductor. And so what we want to do here is sort of come back to that idea and see if we can quantify exactly how quick these charges are going to redistribute from the volume to the surface of a material when we apply an electric field. And so in order to do that, we're going to combine several of our previous equations. So we're going to use the point form of Ohm's law, which is J equals sigma E, Maxwell's first equation, so divergence of E is equal to rho V over epsilon. So that's slightly different from what we've seen before, and I've just used our relationship between our electric flux density D and our electric field to get it in terms of electric field. And then finally, we're going to use a continuity equation from our previous video. Okay, so let's start with the left side of our continuity equation. So we know we have our divergence of J, and now from our Ohm's law, we know that our J is equal to sigma E. So I can write this as the divergence of sigma E. So let's say this is from Ohm's law, this first sort of relationship here. And so now we know some relationship between E and our charge density, or our volume charge density, using Maxwell's first equation. So I can say that this is going to be the divergence of sigma E is equal to sigma times rho V over epsilon. And so that's using our Maxwell equation. So now sort of bringing this all back to our continuity equation, I can say that that has to be equal to negative the partial derivative of rho V with respect to rho T. So again, that's using our continuity equation. Okay, so now what I want to do is I want to focus sort of on the rightmost relationships here, and I'm going to rearrange that and we're going to get a differential equation. So I can have partial of rho V with respect to T plus, and then our sigma over epsilon is sort of our constant, and that's going to be multiplied by our rho V, and all of that is equal to 0. And so this is a differential equation, and we can solve that for our rho V. So let's just say differential equation, and we want to solve for rho V. And so we're not going to go through how to do that, but of course, as you know from previous classes, we would expect the solution to this to be in the form of an exponential. And so what we get then is that our volume charge density rho V is equal to rho V naught exponential of negative T over capital TR. And so that's going to be our expression for our volume charge density as a function of time. So let's define a couple of things here. So first, let's start with that rho V naught out front. So this is just going to be our initial volume charge density. So if we think about a metal that's just sort of sitting there, nothing's happening, and then we apply an electric field across it, our initial volume charge density would be how much charge do we have in that volume, or how much charge do we have in the metal per unit volume initially before application of electric field. So the next important quantity we're going to look at is that T sub R. So that T sub R is actually going to be our relaxation time, and so that is going to be a constant which is equal to epsilon divided by sigma. So we see it's dependent on our material properties, and so this is our relaxation time. So relaxation time. And so what we mean by relaxation time is how long does it take that charge in the volume to move to the surface? Because again, we talked about that's essentially what's going to happen if we have an electric field. It's going to be sort of forcing those charges from the volume to the surface. On a metal, in a dielectric, of course, what we can think of happening is we're going to have, if we have some free charge, that's going to be applicable. Otherwise, of course, the electric field is just going to be polarizing our material. Okay, so what we can then think about is sort of that, again, that specific case of introducing some charge at an interior point. So let's say now we're introducing charge at some interior point of a material. And so this material can be a metal, it can be a dielectric, so whatever type of material we want to consider. So of a material. And so what that's going to happen is that's going to result in a decay. So it results in decay of our rho v as our charge moves from interior to surface. And so essentially that's just writing out explicitly what I was describing earlier. And so we can see that from the equation, of course, because we have this negative in our exponential for our rho v. So initially it's equal to whatever our initial charge density is, and then it's decaying towards 0. And where is that charge going? Well, if our volume charge density is going to 0, then our surface charge density is increasing sort of inversely proportional to that. Okay, and so we can talk about sort of rough time. So of course this T sub r right here, is sort of giving us an idea of how quickly this is happening. So what we can say is that for a good conductor, so if we have a good conductor, so a really good metal, then we're going to have a short relaxation time. So short T sub r. And so we could go through and we could find in the appendix some epsilon and sigma values for a metal, and we could plug into that equation and then plug into our rho sub v equation up here. But what we're going to see is that how short do we mean when we mean short? Well, it could be as short as attoseconds. And so atto is 10 to the minus 18. So we're talking extremely, extremely short. And so we can see how when I mentioned in a previous video that the redistribution for a metal is essentially instantaneous, that that's not a bad approximation. So on the other hand, we could consider good dielectrics or good insulators. And so in this case, we're going to have a longer relaxation time. And again, it's just because if we think about an insulator, it's not letting our charge move as easily through it. And so again, there's a lot of variation depending on our relative permittivity and our conductivity, but this could be on the order of days. So we see a really big sort of difference between our behavior with relaxation time for our metals or our conductors and our insulators or dielectrics.